Welcome to the General Chemistry 2 class. This section is on electrochemistry. This lesson is about balancing redox reactions by change in oxidation number method. Let's begin. In this lesson, we will balance redox reactions using the change in oxidation number method. In balancing redox reactions, there are two criteria that must be met: mass balance and charge balance. In mass balance, the number of atoms of each type on the reactant side equals the number of atoms of each type on the product side. In charge balance, the sum of charges on the reactant side equals the sum of charges on the product side. Considered in balancing net ionic equations, a balance equation must consist of coefficients that are on their smallest whole number ratio. There are three methods in balancing redox reactions: inspection or trial and error method, change in oxidation number method, and half reaction or ion electron method. Our focus for this lesson is the change in oxidation number method. Balancing by inspection method is thoroughly discussed in Chemistry 1. You may refer to the following lesson if you want to recall how to apply this method in balancing equations. Mastery of balancing equations by inspection is useful in this lesson. In the change in oxidation number method, a reaction is balanced by making the increase in oxidation number of an element equal to the decrease in oxidation number of another element. This method is helpful in balancing redox reactions that are not easily balanced by inspection. Steps in balancing redox reaction by change in oxidation number method. Number 1. Write the unbalanced equation. 2. Assign oxidation numbers to all elements or atom types. 3. Draw a line connecting two elements involved in the increase in oxidation number oxidations and the two elements involved in the decrease in oxidation number reduction. Note the changes in oxidation numbers per atom. Number 4. Determine the multipliers that will make the increase and decrease in oxidation numbers equal. Consider these multipliers as coefficient of the substances directly involved in the redox reaction. 5. For the other elements in the equation, perform balancing by inspection. Example number 1. Balance the equation corresponding to the reaction of chromium chloride with tin chloride, which yields chromium chloride and tin chloride. Solution number 1. Write the unbalanced equation. 2. Assign oxidation numbers to all elements. Take note that all compounds are chloride salts. Thus, the oxidation number of chlorine is -1 for all compounds in the reaction. 3. Note the changes in oxidation numbers per atom. Note that chromium and tin undergo changes in their oxidation numbers. Chromium decreases in oxidation number by 1, which means 1 electron is gained in the reaction. This suggests that chromium-3 chloride undergoes reduction. Thus, it is the oxidizing agent. On the other hand, tin increases its oxidation number by 2. This means 2 electrons are in the reaction. With this tin-2 chloride undergoes oxidation and it is the reducing agent. 4. Determine the multipliers that will make the increase and decrease in oxidation numbers equal. Multiplying the decrease in oxidation number of chromium by 2 and the increase in oxidation number of tin by 1 gives us equal changes in oxidation numbers. We should focus only on the magnitudes of changes and ignore their signs. Consider the multipliers as coefficient of the substances involved in the change in oxidation numbers. The multiplier 2 in the decrease of oxidation number of chromium should be the coefficients in chromium-3 chloride and chromium-2 chloride. On the other hand, there is no need to adjust the coefficient of tin-2 chloride and tin-4 chloride since the multiplier is just 1. For the other atoms in the equation, perform balancing by inspection. And at this point, chloride is already balanced. With this, the equation is already balanced. Example number 2. Copper metals react with nitric acid to produce copper-2 nitrate, nitric oxide, and water. Write the balance equation for the reaction. Write the unbalanced equation. In many cases, it is better in balancing that salts and other strong electrolytes, strong acids and strong bases are rated in a way that ions are separated from each other. We can convert this resulting ionic equation to the formula equation once you are done balancing. Number 2, assign oxidation numbers to all elements. Identify the elements that change in oxidation number. 3. Note the change in oxidation number per atom. Copper increases in oxidation number by 2, implying that 2 electrons are lost by the element in the reaction. Thus, copper metal undergoes in the reaction and it is the reducing agent. On the other hand, nitrogen in nitrate ion decreases in oxidation number by 3, which means that 3 electrons are gained by the element in the reaction. Therefore, nitrate ion or nitric acid undergoes the reduction and it is the oxidizing agent. Determine the multipliers that will make the increase and decrease in oxidation numbers equal. To make them equal, multiply positive 2 by 3 and negative 3 by 2. Consider the multipliers as coefficients of the substances involved in the change in oxidation numbers. The changes in oxidation numbers can be balanced by multiplying the increase in oxidation number by 3 and the decrease in oxidation number by 2. With this, the coefficients of elemental copper and copper 2 ion must be adjusted to 3, while the coefficients of nitrate ion and nitric oxide must be adjusted to 2. 5. For the other atoms in the equation, perform balancing by inspection. On the product side, since 1 mole of copper 2 nitrate consists of 1 mole of copper 2 ion and 2 moles of ion, 6 moles of nitrate ion pair with 3 moles of copper 2 ion. As a result, the number of moles of nitrate ion on the reactant side increases by 6. Thus, its coefficients become 8. On the reactant side, 1 mole of nitric acid has 1 mole of hydrogen ion and 1 mole nitrate ion. Thus, 8 moles of hydrogen ion pair with 8 moles of nitrate ion. The coefficient of nitrogen ion is adjusted to 8. On the product side, adjust coefficient of water. This step also balances oxygen. Converting the ionic equation into the formula equation gives us the balance equation. Rechecking allows us to see that the number of atoms of each kind on the reactant and product sides are equal. Example number 3. The formation of iodine in the aqueous state can be formed through comproportionation between sodium iodate and sodium iodide in the presence of hydrochloric acid. Sodium chloride and water are the other products of the reaction. Write the balance equation for the reaction. Solution number 1. Write the unbalanced equation. We can separate the ions for the strong electrolytes, sodium iodate, sodium iodide, hydrochloric acid, and sodium chloride. Note that on the reactant side, sodium ion is written once since it is just a spectator ion or an ion that is not directly involved in the redox reaction. Solution number 2. Assign oxidation numbers to all elements. Solution number 3. Note the changes in oxidation numbers per atom. Iodine in iodate ion decreases in oxidation number by 5, implying that 5 electrons are gained in the reaction. Thus, iodate from sodium iodate undergoes reduction and it is the oxidizing agent. On the other hand, iodide ion increases in oxidation number by 1, which means 1 electron is lost in the reaction. Therefore, iodide ion from sodium iodide is oxidized in the reaction and it is the reducing agent. Notice that the reaction is comproportionation since oxidation and reduction of 2 different reactants produce the same product, which is diatomic iodine. With this, we can write the comproportionation product to avoid confusion and adjusting coefficients. Likewise, in this proportionation, we should write twice the reactant undergoing this reaction. Solution number 4. Determine the multipliers that will make the increase and decrease in oxidation numbers equal. We can balance the changes in oxidation's number by multiplying the decrease in oxidation number by 1 and the increase in oxidation number by 5. Consider the multipliers as coefficients of the substances involved in the change in oxidation numbers. With this, the coefficient of iodate ion is not adjusted since the multiplier is 1, while the coefficient of iodide ion is adjusted to 5. We are looking into changes in oxidation numbers per atom. So the coefficients of diatomic iodine must be the multiplier divided by 2 since diatomic iodine has 2 iodine atoms. Hence, the coefficients 1/2 and 5/2 for the first and second diatomic iodine respectively. Solution number 5. For the other atoms in the equation, perform balancing by inspection. Reactant side, coefficient of sodium ion must be equal to the sum of coefficients of iodate and iodide ions, which is 6. Product side, adjust the coefficients of sodium ion to 6. Reactant side, 1 mole of sodium chloride has 1 mole of sodium ion and 1 mole of chloride ion. Thus, 6 moles of chloride ion pair with 6 moles of sodium ion. Product side, adjust the coefficients of chloride ion to 6. Reactant side, since 1 mole of hydrochloric acid consists of 1 mole of hydrogen ion and 1 mole of chloride ion, 6 mole of hydrogen ion pair with 6 moles of chloride ion. Product side, adjust the coefficients of water to 3. Convert the ionic equation to formula equation. Notice that the 6 moles of sodium ion are distributed to 1 mole of iodate ion and 5 moles of iodide ion. We must combine the two terms of diatomic iodine. Combining 1/2 and 5/2 gives us 3, hence the resulting coefficient of diatomic iodine. We now have the balance equation for the reaction. By checking, we can see that the number of atoms of each kind on the reactant and product sides are equal. To summarize, in balancing redox reactions by the change in oxidation number method, coefficients are adjusted in a way that the increase in oxidation number of one element is equal to the decrease in oxidation number of the other element. The coefficients of substances not directly involved in the electron transfer can be balanced by inspection. Welcome to the General Chemistry 2 class. This quiz is about balancing redox reactions by change in oxidation number method. Let's begin. Number 1. Number 2. Number 3. Number 4. Number 5. Number 6. Number 8. Number 9. And number 10. Thank you.